everybody. I'd like to thank you all for joining the DGrav seminar this week. This is the last DGrav seminar of the semester, and we'll keep you posted on updates for seminars next semester. So I'm Deborah Ferguson, a postdoc at UIUC, and I'll be chairing today. I would just like to remind everybody of the code of conduct. So please be mindful and respectful of the speakers, as well as of each other when asking questions and discussing. So just be respectful. Now, I would like to welcome our speakers, Professor Alessandra Papa and Dr. Benjamin Steltner from the Max Planck Institute for Gravitational Physics in Hanover. Today, they're going to be talking to us about continuous gravitational waves, more specifically searching for continuous gravitational waves. So as I said, our first speaker is going to be Professor Alessandra Papa. She is currently a Max Planck Research Group Leader in Hanover. She got her PhD from the University of Rome Tor Vergata, and then since then has been in a number of places, including the Max Planck Institute in Golm, University of Wisconsin-Milwaukee, University La Sapienza, Leibniz University, and she's also an APS fellow. So after she gives an introductory talk, we will then have Dr. Benjamin Steltner, who recently got his PhD from Leibniz University, Hanover, and is now a postdoc at the Max Planck Institute. So let's welcome our speakers and let them go ahead. We will save questions for the end. We'll have a discussion session at the end where you guys can ask your questions after both speakers have given their talks. But if you have clarifying questions, short, quick things, you can feel free to put them in the chat or raise your hand during and ask those, but save main questions for the end. All right, and now I will hand it off to Professor Alessandra.
Great. Well, thank you so much for the nice introduction and for having us here talk this afternoon about our favorite topic, continuous gravitational waves. So when talking about continuous gravitational waves, most people think about these glorious signals that have been detected for the past few years. These are, as you all know, I'm sure, the binary in spiral merger signals. And here, the reason why I'm showing them is that you can see from the x-axis what the time scale for the duration of these signals is. And it's basically tenths of seconds to seconds. And that's the main distinctive feature with respect to the signal that we'll be talking about tonight, which is a continuous gravitational wave signal, a signal that's virtually always there. So these have not yet been detected, unfortunately, but when they are, they will open possibly a new branch of gravitational wave astronomy. It will be in the same relation to these signals, to the binary signals, as transient astronomy is to pulsar astronomy. So continuous waves could be the next big thing. And in their simplest and most probable form, they will come from spinning neutron stars. And the simplest model is that of the spinning neutron star having a deformation from a perfectly axisymmetric shape. And because it's spinning, then it has a varying quadrupole moment that produces gravitational waves that are always there, emitted steadily as long as the deformation is sustained and the star continues to spin. The emission will be at a frequency which is twice the rotation frequency. So if it's the ellipticity, this quantity here that I've indicated with epsilon, that is sourcing the waves, it's a very important question to ask, what could possibly source the ellipticity? Well, if the object, as a neutron star, an isolated neutron star, is born in a process that's quite messy, supernova explosion and core collapse. And in this messy process, it's not unreasonable to imagine that there is some non-axisymmetry that could be sort of frozen in from the birth process. There are star quakes that we know neutron stars undergo. These are usually invoked to explain, for example, giant flares that are observed from these objects, and are usually connected to like mechanical failures of typically the magnetar crust. And these could trigger a sudden reconfiguration that could produce an ellipticity, a wrinkle. Internal magnetic fields could produce the deformations of the main sort of core of the star, the internal part of the star. And if the neutron star is actually accreting from a companion, this is a very interesting case, since it's accreting through material, through the magnetic field lines that funnel these accretions and then accrete on a rather limited area on the object. This naturally sort of creates an asymmetry, and there could be ellipticities, and so deformations through density variations associated with the accretion process. It's been long known, and I'll take here a very quick deviation talking about accreting neutron stars, so that if you look at the distribution of the spin frequency of neutron stars, so if you squint at this histogram, you might see actually that it's a bimodal distribution, but certainly without too much squinting, everybody recognizes that it's abruptly cut off just above sort of 700 hertz. And that's remarkable, because actually the accretion process could, in principle, drive the spin rotation of the star to much higher frequency, because the neutron star could certainly support rotation frequencies that are faster than 700 hertz. So it's been put forward as a proposal that there must be some kind of balancing mechanism, some balancing torque that can balance the accretion torque. And the idea is that it's actually gravitational wave emission, that gravitational waves that could provide this balancing mechanism. The fact is that since the gravitational wave torque scales with a high power of the frequency, this would actually also qualitatively nicely explain why there is such an abrupt cutoff in frequency. And this is not a new idea, but more recently than when the idea was first proposed, Gittins and Anderson have actually done a rather thorough study considering different spin evolution models with different type of gravitational wave balancing torques. So due to various mechanisms, mountains or R modes, and they find that basically, or no balancing mechanism with gravitational waves, that the only way to produce a distribution of spins that is even remotely comparable and similar to the one that's observed is if you have gravitational wave emission. So continuous gravitational waves could actually explain one of the open questions in regarding the spin distribution of LMXPs. Okay, so let me go back to the ellipticity. What could source it is something I just discussed. And what about the actual magnitude of this deformation? Well, people who model neutron stars and particularly think about this problem prefer to think about two simpler problems that are still interesting for us who want to make observation. And namely, One is, what is the maximum ellipticity that a neutron star could sustain? That's interesting, obviously, because if that value were very, very, very low, this would mean that signals are rather unlikely to be detected. And the maximum ellipticity is a bit easier to compute, because one can relate it to the maximum deformation that the crust can sustain before it breaks. Unfortunately, that in turn, though, still depends on the details, or at least basically the breaking strain, yes, of the crust, which depends on the internal composition of the object. And so, at the end of the day, the values differ by as several orders of magnitude, depending on what one can imagine the object is made of. The smallest ellipticity is basically due to magnetic fields. So if the deformation is solely supported by magnetic fields, well, we are at ellipticities that can be as low as 10 to the minus 14. So basically, the ellipticity values span something like 10 orders of magnitude, from 10 to the minus 4 to 10 to the minus 14. And it's useful to keep these numbers in the back of your mind, because Benjamin later will actually present results and talk about limits and constraints from observations that we can put exactly on this quantity. Now, continuing to think about the ellipticity, in 2018, Won and collaborators put forward an interesting suggestion that's summarized in this plot, where you can see a PP dot diagram for known pulsars, and these are the points in the plot. And actually, the black points are the measured value, but the sort of bluish circles are the corrected values when they've tried to actually evaluate the intrinsic spin down of the object. So removed any effect that could be due to motions, relative motions. Okay, and then superimposed here, we have lines of where we imagine objects that evolve in frequency due to either solely a mission of gravitational waves due to ellipticities. And these are the 10 to the minus 8 and the 10 to the minus 9 sort of orangey lines, and objects whose frequency evolves because of gravitational waves, so due to an ellipticity, and to a dipolar magnetic field, and with fields of different in sort of strengths. And you can see here that when the field gets to about 10 to the 7 Gauss, basically the spin evolution is the same as that for an object, for a gravitar that only evolves due to gravitational wave emission. And the thing about this plot is that it is suggestive that there's actually, no objects below the 10 to the minus 9 line. And so this suggests that actually there is a minimum ellipticity at 10 to the minus 9 for population of objects that actually evolve only due to gravitational wave emission. Okay, so this 10 to the minus 9 in this range that I was talking about before, between 10 to the minus 4 and 10 to the minus 14, is a sort of interesting milestone value, because there might be some observational evidence that that's a sort of a minimum value for the ellipticities of pulsars. There's also other emission mechanisms, not just quadrupolar deformations. For example, if we have an oblate spheroid, so an object that's spinning, and because it's spinning, it's got a slightly oblate shape, that in itself, it was spinning aligned with the principal symmetry axis, it would not be emitting gravitational waves. But if the spin axis is not aligned, then it's emitting at a frequency that's very close to its rotation frequency because it precesses. There's also R modes. R modes at a very basic level are related to oscillations of sort of the material which the star is composed in rotating stars. And so these cause variations in the distribution of mass of the neutron stars, and this is what generates gravitational waves. The frequency of gravitational waves due to R modes is 4/3 of the rotation frequency. So you can see that depending on the emission mechanism, there is a different relationship between the gravitational wave frequency and the rotation frequency. So if we did detect continuous gravitational waves, well, what could we learn? Well, if we knew the distance of the object that's emitting gravitational waves, and we knew that the emission was due to a deformation, we could know something about the deformation of the object, and that is somewhat related to the internal structure of the neutron star. In principle, there's 100 million neutron stars in the galaxy, which we know of from the light and radio observations of about, a few thousand. So in principle, this is another tool to have access to the population of neutron star, and it could give us access to a population that's invisible with electromagnetic radiation. The signal is always there, and it allows very precise measurements and remeasurements. And we know that with pulsars, because of this, exquisite tests of GR have been done. This would be a completely different probe, and in fact, a non-GR polarization tests have already been proposed. In conjunction with electromagnetic observation, as I was saying before, just by comparing the frequency of the gravitational wave and of the electromagnetic of the rotation of the object, one could understand what the emission mechanism is. Is it R modes? Is it precession? Is it a mountain? One could even, if the difference is not too big, even understand if perhaps there is a differential rotation between the core of the star that might be sourcing the gravitational wave emission and the surface of the star that's responsible for the EM emission. And even more intriguing, perhaps, if the signal does not come from a neutron star, there's various signals that are continuous that would not necessarily have to come from a neutron star, but for this talk, we're going to stick with this more standard scenario. The signals are very weak. If you plug into the amplitude formula that it's here, and numbers that are sensible, and for the distance here I've used 1 kiloparsec, so it's important here to understand that we're talking about galactic objects, so we absolutely at least for now do not hope to see anything that's outside of our galaxy. We get amplitudes, so strain amplitudes that are something like 4 orders of magnitude below the CBC signals that are currently detected. So the question could be, how could we possibly ever hope to be able to see them? Well, in essence, the idea is very simple. How do you detect a weak monochromatic signal generally? Well, you take an FFT, you take the power, the square modulus, and then out pops the signal, a peak at the frequency of the signal. And this is basically what there is to doing continuous wave searches. You basically construct a glorified power as a detection statistic in the frequency domain. And the fact is that the longer is your FFT baseline, the higher is the SNR. And so you would like to observe for a very, very long time. But the fact is that if you don't know what the waveform is, you have to try many different ones. And what determines the different waveforms is, of course, the different intrinsic frequency and frequency evolution, possibly of the signal, but also in the way that we receive it, what different position in the sky it's coming from. And Benjamin will come back to this. So in the end, as you increase your observation timeline, which you want to do in order to increase the SNR, the number of resolvable waveforms grows very quickly, and it very quickly becomes very high. So with 6 months of data, if you want to search a few hundred hertz, and you want to search the whole sky, so allow the signal to come from anywhere in the sky, you have to do something like 10 to the 28 FFTs, and this is not possible. So optimal methods, the fully coherent ones, the FFT, cannot be used. And so basically, the name of the game is you've got these computing resources that are limited. You can't do your 10 to the 28 waveform search. You have to make some sort of sacrifice. So do you sacrifice depth, or do you sacrifice breadth of the search, or some combination? And the fact is that no one knows what the winning trade-off is, because we don't know what is the signal out there that would be first detectable. So many different searches are carried out, and each reflect a different trade-off, and it's highly optimized. So these are not searches that are simple and that, you know, you can quickly turn knobs. Depending on what trade-off you make, you basically design a search around it. And this is why often with every different data set, you'll see a whole slew of different searches. And here I just had fun trying to find the latest continuous wave searches. And these are just the ones that cover broad parameter space, broad parameter spaces where we have this problem. And so in this talk today, we're going to talk about the searches, the trade-offs, particularly that we have done in the Einstein at Home volunteer distributed computing project searches. And this is what Benjamin is going to tell you about next, and putting them also into context. So I'm going to hand off the mic to Benjamin.
Thank you very much. Hello, everyone. So let me take one step back to the waveform, which in principle, when it comes from the neutron star, is just a sinusoidal signal. But since the gravitational wave detectors are on Earth, we get the Doppler modulation on a daily basis from Earth's rotation around itself, and a yearly modulation from Earth's orbit around the sun. And if the source, so the neutron star, is also slowing down its rotation, we speak of spin down. So as you can see in the yellow curve, the frequency over time decreases. And since it's Doppler modulation, this means that the waveform for every sky point looks a bit different. Which are shown in this plot. These are continuous waves, all with 100 Hertz frequency, no spin down, and just different sky positions. And as you can see, these waveforms just look very different. So we use advanced LIGO, so gravitational wave detector, and we use the open data of that. We are looking at the time series, h of t, or also strain, which is these differential arm length differences. So if a continuous wave passes through, this imprints itself on the strain. advanced LIGO takes scientific data in so-called observation runs. These are 6 to 18 months or so long, whereas the longer ones are split into sub-runs. So for example, O3 was 12 months roughly, and was split in O3A and O3B, which is roughly 6 months each. The policy for publicly releasing the data is so far always 18 months after the end of the run. And since we're not part of the LVK, we are always looking at a delay of 1.5 years or so. As Meb already mentioned, for such a long duration of data, there really are a lot of waveforms resolvable. And you can also say it as that the resolution with which you need to search over scales with a high power. For all scale searches, it's usually the time span of data to the power of 5 or 6, depending on the search. So how would we do a search for an unknown target? Well, we take some waveform, which is characterized by the template, so which frequency, frequency derivative, and which sky location. In principle, one could also take further spin derivatives, but this is computationally exhausting enough already. So usually only the first order spin down is taken. You phase correct the data and then basically take or compute some power, which is a bit simplified. You save that as a candidate, where you save what template did I search and what is the detection statistic. So how likely is this template due to a continuous wave? And then repeat this 10 to the 28 times, which, as Meb already said, is not really possible. So let's pretend this would be possible. We arrange these templates in some grid. And I mean, there can be multiple grids. So how could we compare them? Well, one thing is the runtime, which is a function of, or some function of the number of grid points. So in principle, for each grid, we could access how costly would it be to search that. Another important quantity for our grids is the so-called mismatch, which is 1 minus the signal power loss due to us computing the power not directly on the signal parameters, but on a grid point somewhere close by. So we could, in principle, arrive at the optimal grid. For all the grids, we compute the runtime and take only these which are affordable for us, and for those take the best one, or take as the optimal, the one with the lowest mismatch. But unfortunately, for a coherent search, there really is no grid which is computationally affordable and which doesn't lose all signal power, which is equivalent to saying that a coherent search, as already mentioned, is infeasible for that large amount of waveforms. So what we are doing instead are so-called semi-coherent searches. We take the full time span of data and split these into segments. Each segment is of a duration tco, so coherent time, and each segment is analyzed coherently and then combined incoherently. This has the great advantage that the computational cost, or that the resolution within each segment only scales with the 5th power of this coherence time. And we do this number of segments times. So this is vastly faster or lower in computational cost than the time spent to the power of 5. However, we do lose some sensitivity that way, which, however, due to the vast amount of computational resources saved that way, makes it very worthwhile. So there are basically two knobs, or two important knobs to tune such a semi-coherent search, which is firstly the coherence time and this mismatch. So sort of what underlying grid is there. And here I show again the FFT example. One has to take into account that when one goes to higher tcos, the peaks get narrower and narrower. So to get the same signal power loss by being slightly off the peak, we need to increase the resolution quite a lot. So choosing a tco often is kind of a balancing act, where the signal to noise ratio does increase with the square root of the coherence time. But to get a constant mismatch, so the constant signal power loss, we need finer and finer resolutions. And since we are in 4 dimensions in our search space, the computational cost for finer resolutions grows very, very quickly. Also, the trials factor increases. So if we find anything, this is then less significant. Another thing to keep in mind with the increasing of TICO is that one becomes less and less robust against non-ideal waveforms, where although for pulsars, we know they are quite stable, I mean, the universal clocks, but still for pulsars, or for some pulsars, we know that they glitch. So a rapid increase in frequency with some relaxation time. And this is something one has to keep in mind when increasing the TICO. Another important aspect when designing a search is, of course, the parameter space, which one wants to search over. I show here a few different latest O3 all-sky results. Of course, all are all-sky, so I don't show this. And I show here the frequency and the spin-down range. Let's split them apart. And there really are a few different ways or choices one can do in setting up all-sky searches. So for example, in the top left, the frequency half goes for a very vast parameter space, 10 to 2048 Hertz, a vast spin-down range, but sacrificing in sensitivity there. When comparing to known neutron stars, so mostly the pulsars known electromagnetically, where we see the spin down, I'll come a bit later to this as well. This range is likely a bit too broad, but I guess in an eyes wide open approach, if there would be a continuous wave there, it would be very interesting results where then probably some population studies would, get some interesting results out of that. Also to note that going up to 2048 Hertz is very high frequency, where notoriously with increasing frequency, it gets harder and harder or more costly and costly to compute the resolution. So on the other hand are sort of the searches which restrict itself to smaller parameter spaces, and instead investing the computational power in a narrower parameter range to gain some sensitivity. And there, for example, it's often that the spin down range is quite limited, but looking at the pulsars and the distribution of the spin down there, one sees that most of the ones we see are at very tiny spin down, so they sort of make a bet that if we find a signal, we will find it there first, and therefore do so with the increased sensitivity. There are also other searches which are more robust against these deviations from the ideal waveform. So these glitches, where, for example, SOAP allows for some spin wandering in the frequency. There are also very fast searches. So there really is a lot of different choices you can make, which then basically also reflect on your results. What we went for with our search is sort of a middle ground in the parameter space, 20 to 800 Hertz. It's more or less in the very sensitive region of the detectors. It doesn't go up to a very high frequency, which are very expensive to compute. And also our spin down range is sort of middle ground between this very broad ranges of 10 to the minus 9 and 8 and the smaller regions. We also spent quite a lot of computational power to dig as deep as possible in the parameter range we chose. And we facilitate this by a comparatively long current time of a few days and running these searches for months. So as a slight motivation for the spin down range, we see here, as mentioned quite often already, the known pulsars from the ATNF catalog. In gray is the region which is not visible by ground-based gravitational wave detectors. And although there are some pulsars with spin down up to 10 to the minus 9 hertz per second, most of them are at very tiny spin downs. Okay, so to give you an idea about the compute cycles, our latest published ORSCHI searches required something like 10,000 years, or the equivalent of 10,000 years on one CPU core, or the equivalent of 2,000 years on one GPU. And with these two great machines, which are Atlas and Einstein Home, it was possible to complete these searches in 6 or respectively 12 real months of time, where Atlas is a computer cluster located also here in Hanover in our basement, which is just shy a bit of 100 logical CPU cores and has 2,400 GPUs. So coming to Einstein Home, our second sort of compute resource. This is a distributed volunteer computing project on the BOINC infrastructure. You may or may not know it from City at Home, where volunteers, you and me, my grandmother, I don't know, can sign up and then donate the compute cycles to advance basically our science case. And they get credits for that. So if you want to join, there's the website, but shameless plug. So how does this work? So we have our parameter space. In the latest search, we needed 10 to the 19 templates, so 10 to the 19 waveforms to cover the parameter space. And we basically sent one program, some necessary data, and a subset of this parameter space to these volunteers, where we call this one work unit. So every time my grandmother's PC is idle and wants to do some science work, it gets sent one of those work units, which covers like something like 10 to the 11 templates and runs for, in the GPU case, half an hour, and in the CPU case, often like 8 hours or so. Of these 10 to the 11 templates, 30,000 candidates are returned. So 30,000 waveforms with the associated detection statistic, how likely is it or not, where, of course, the 30,000 candidates are the most likely waveforms. So all in all, back to our servers, make 10 to the 12 candidates, which is something like 20 terabytes of data. So setting up such a search is quite delicate. Firstly, the volunteers trust us with their donated computational cycles. So it's really important, especially because these searches run for months in such a parallel fashion, to really optimize every single bit about this search. So we do a lot of optimizations into the data preparation, in the data cleaning, and especially in the search setup, which is actually not that easy, since also the volunteer computers are quite different. Whereas in a computer cluster or so, you often have more or less the same systems. The volunteer computers are very, very different. It starts from different hardware. You have the ultra gaming PCs, which are very fast. You have the standard office PCs down to quite old hardware. So you really have to think about what, for example, what memory these systems can afford. And not that we send some jobs to them, which then fry the system. I mean, they are not really fried, but get slow very, very quickly. Also, the software is quite different. Whereas in a computer cluster, it's, I guess, guaranteed that it's one operating system or so. I guess we have like everything, especially the different libraries, etc. So where I told you that, we have one program and they get the data and the subset of waveforms. we have many different programs compiled for all the different operating systems, which is frankly something which I'm very glad I don't have to do, but we have the support stuff for that. So thank you for that to them. Also, when one designs a search, one would like to know when this is finished, because if we design it for 12 months and we're off by a factor of 2, we are already looking at a runtime of 2 years, at which point the new data is already out. So then we could immediately start the new run, but runtime estimation, I mean, with all the different hardware and software is difficult already, but sometimes it feels a bit like crystal ball reading. Then you have a heat wave, so people turn down their PC because the room gets too hot. In Europe, we had the energy crisis, so people powered down their PC to reduce the energy footprint. New hardware is released, which increases the speed, but then the hardware does not really get through because of some chip supply shortage. So that's very difficult, but so far, I think we were always in the correct month. Yeah, map not so perfect. And lastly, there are also bandwidth limitations. As mentioned, we need to send the data to the volunteers and we get these results back. So it's basically an interplay between the result file size and the average job duration so that our servers can handle this. And lastly, there are also storage limitations. As mentioned, these 10 to the 12 candidates, it's something like 20 terabytes of data. So this we need to save for a long time and also need to post-process that. Speaking of the post-processing, so we have these 10 to the 12 candidates, and the first very crucial step is called clustering, where we group these 10 to the 12 candidates and filter out the 3.5 million most promising, which then go into a hierarchical search with multiple stages, where each stage basically is a search which is ever more increasing in sensitivity. So increasing coherence time and or reducing the mismatch, so going to finer and finer grids. And this becomes possible by rejecting candidates at after each stage. So we sort of zoom in the most interesting regions, and we can do this ever more finely by narrowing down these sort of interesting regions. At the end of this whole search scheme, only 6 candidates remain. And these 6 candidates were 6 of the 7 hardware injections, which were in our search range. So hardware injections are fake signals put into the detector at the hardware level by actually actuating the mirrors. And this is great for pipeline validation purposes. So we know that a real signal would also survive the data acquisition, the data preparation and cleaning process, and in the end, survive the pipeline. And I think a sort of trademark of continuous wave searches is the precision with which we recovered these hardware injections, which is within 3.6 arc seconds in the sky and some nanohertz in frequency. So if we find something, we can, for example, give astronomers quite precise parameters where to look for example, for pulsations, which would be a great cross-validation if we find that first. Unfortunately, in our search, no astrophysical candidates were left, so we set upper limits on the gravitational wave amplitude. Or sort of other way around, what is the smallest continuous wave amplitude that would have survived the pipeline? So we can exclude gravitational waves with higher amplitude because otherwise we would have seen them. These plots usually look like these. So the sensitivity or the upper limit always follows the sensitivity of the detectors. I show here in gray the 4 pipelines of the LVK. In the gray diamond is a recent power flux O3 search, and in blue the Falcon search, and in red finally our search. I'm hiding some of these upper limits here to visualize something, namely the trade-off these searches do. I show here the frequency half pipeline, which was this very broad 10 to 2048 hertz and very broad spin down range. And one could look at these upper limits, say, well, our search performed better. But actually, it's not only that two-dimensional, but one has to really take the parameter space which was searched into account, which I tried with this. Yeah, it works. So one has to keep in mind in what parameter space these upper limits actually apply and exclude continuous waves. I think I've skipped that. So with the upper limits on the continuous gravitational wave amplitude, one can also now set upper limits on the neutron star ellipticity. Map showed these equation already, so I won't explain again. But for different distances, we can basically exclude the ellipticity of the neutron star. So for example, for a neutron star spinning 150 Hertz, so gravitational wave frequency of 300 Hertz, we can exclude ellipticities at or greater than 10 to the -7 level, nearer than 100 parsec, which for the canonical moment of inertia for a neutron star and radius of 10 kilometers is on the millimeter scale, which I find always very fascinating. And if you can remember the distance scale, I say something different here, so not good. The distance scale is like 10 orders of magnitude on this ellipticity from -14 to -4. So we really probe interesting regions and plausible regions, which will even be more interesting with new data. I think we are running a bit late, so I'll skip this as well. And just to mention for the future, a colleague of us did some detectability study from population synthesis of non-recycled pulsars, neutron stars, what can we expect for the future? So one thing is, where could these systems actually be? So could we do an all-sky search, but instead target the disk more, meaning spend more computational power on the disk and less on the less interesting regions? And where do we, or where should we put our computational power in the frequency and spin down range? And lastly, did also some detectability study with O3 data and next generation Einstein telescope and Cosmic Explorer, where basically not the chance of detection, but the number of detections on the order of 1. Chance of detection at number of 1 would be great. So with this, I want to come to the summary. I hope I could convince you that there really are many ways to do continuous wave all-sky searches, making different assumptions, different choices, different trade-offs, and sort of the results are complementary to each other. I hope I could also convince you that although the signal waveform of a continuous wave is quite trivial, the searches are very hard and work-intensive to do, as well for the humans as for the computers. And I would like to thank the volunteers of Einstein Home and the Atlas cluster that allows us to probe deep into the parameter space region we deem interesting, yes, and which allows us to reach these interesting ellipticities. And with this, I thank you very much for your attention, and we are taking questions now, I guess.
Okay, thank you, Alessandra and Benjamin, for that excellent talk. We really appreciated that. All right, yeah, let's open up the floor if anybody has questions for either one. Keith, do you want to go ahead and speak up, or I can read this out loud?
Sure, I forgot that I can actually speak in this this venue. Yeah, I'll just a very nice analysis and presentation, by the way. That was very, very well done by both speakers. Now that you've completed this analysis, have you considered the Falcon approach of focusing on very low spin downs in the nearby galaxy by extending your T-co and making it computationally tractable?
I mean, I don't know how much sensitivity we would gain by that, if it would really be such an improvement. I think, yeah, probably going to higher frequencies and covering a bit more parameter space
Yeah, it just occurred to me that you might be able to go to significantly longer coherence times if you scrunch down on the maximum spin down. But it occurred to me also that you may run into problems with the home computers if you're using Einstein Home for this. Not sure how that trade-off works.
Yeah. So, hello. Yeah, so that's no, we actually hadn't thought of this. It's certainly, yes, it's yet another trade-off. I have this nagging unease about increasing further the coherence time even at the earlier stage, because actually, since none of us is detecting anything so far, I'd actually think that we should perhaps go back and find clever ways to look at candidates from the first stages that we then discard because they don't maintain strict phase coherence, and see if we can gain sensitivity in that direction. So your proposal is interesting, but it's kind of orthogonal, right? It says limit the spin down range to the low ellipticity sources, and for those go even deeper, which really means longer TCO, so requiring strict phase coherence even from earlier on. So it's interesting, but no, we hadn't thought about it because of this kind of basic unease that I have with these pretty long TCOs, even for these searches here.
Okay, I understand. It wasn't a proposal, just wondering if in those lines. Okay, thank you.
All right, any more questions out there? Anybody? Okay, well, I may have missed this on a slide, I'm not sure, but how many people / computers do you guys have like signed up for the Einstein at Home?
That is like very good question. I mean, people are signing up and people are sort of fading out and coming back.
Yeah, tens of thousands signed up, right?
Yeah.
But active?
Active, yeah.
Yeah, at any given time, I think we have thousands, right, of people actually running the search. So, and that's the great thing, is that sustained 24/7, but it's 1,000 actually working at any given time.
Very cool, very cool. Oh, Charles, you want to speak up? Otherwise, I'll just read it out loud.
So, okay. Nice talk. I really enjoyed the presentation. Let me ask the big question. So when might we make a first discovery, and what are the most important variables?
I ask you. Tell me about that ellipticity. Well, I mean, when can we make the first discovery? Well, we hope it's with every new data set. Every new data set, it's like a big Christmas present. And, we turn it around in all possible ways. And perhaps in one corner of this huge parameter space, there is that first signal that opens the field. I think the most important thing, my take would be that we have an EM counterpart, because this would first of all confirm it, and then gives us an insight about what is actually sourcing the signal, and would give us the distance scale. So I think that's the most delicate thing. What do you think?
Yeah, I mean, if it's not like yeah, so let's say a candidate survives the pipeline, then we are kind of out of data. It's a hard it's not like with the CBC signals where the waveform is like super special, and therefore if we see it, it's a bit more significant. I mean, it really is just a sinusoidal signal with Doppler modulation. So in principle, one need to wait for the next observation run and see if it's still there. But is it there because it's still in the detector, or if it's still the signal? So I would say, yeah, having an EM counterpart or also that would be a very strong argument for it.
So we might have possible candidates that take a long time to resolve.
Yeah.
And I must say one thing, that the first CBC signal, the moment that it was known that there was a really serious candidate, the detector configuration was frozen and all sorts of checks started. Now, by nature of continuous waves, this could never happen this way, because we even get to see that there is perhaps a candidate. First of all, we need to have all the data in the can, or a large fraction of it. And then the searches are very intensive. So a lot of time has elapsed since the detector existed that produced the data, and the time when we might want to go back and see is there some coherence at very low level hidden in the hardware, the instrumentation, what's around it that could have produced it. So those validation studies on the detector, I see that as, if we don't have an EM counterpart, these will be delicate, just because the detector might not be there anymore that produced that data.
At least the source will be, configuration might be frozen.
I hope so, at least that.
Okay, any more? Oh, here. Well, okay, now it's just a comment from Keith that Virgo has different instrumental artifacts thrown in the chat. So you mentioned briefly at the very end, Cosmic Explorer and Einstein Telescope. With those, I think you made a quick comment about how likely you expect to see detection there, but I kind of missed it. It was kind of fast. So we're pretty optimistic that with Einstein Telescope and Cosmic Explorer that we'd likely see something.
Yeah, may have misremembered. We are hoping to look at hundreds.
Very cool. It depends on the model.
Depends on the model. Exactly.
Sure.
I was being pessimistic in the model selection. Yeah.
You also showed earlier at one point that some of the frequencies that you would expect that wouldn't be able to be seen by ground-based detectors that were too low frequency, which naturally makes me always think about LISA and space-based detectors. But I know that that's also at a very different sensitivity range of things. Is there any prospect of seeing these with LISA?
No, neutron stars. No. That we need the perhaps some intermediate detector like the SIGO, I guess, could some. But LISA is pretty low frequency.
Right.
And also you see, you remember that for a given ellipticity, so the deformation, the amplitude of the signal scales with the square of the frequency. And so now we're going to low frequencies, which means the same deformation produces a much weaker signal. And so that's another problem.
That makes sense. Thank you. All right, any last questions before we thank our speakers again? All right, well, thank you guys so much for being here. I know it's late for them, so let's give them an extra round of applause. I just want to remind everybody that this is the last DGrav seminar of the semester, but we'll continue next semester, so keep an eye out for information and announcements regarding that. All right, thank you, everybody.
Thank you for having us.
Thank you.
Bye, everyone.
Bye.